So, how are you? Fine? Great. I hope that you are also fine with the subject and my lectures. If not, please let me know, okay? So, first of all, one thing, which is the calendar of the next lectures. So I made some computation and I did some update to this schedule here. And in particular, I noticed one thing. I noticed that I forgot to compute two lectures here on May 5 and May 5 and May 6. They were not listed before, it was a mistake. So I updated the calendar, and this is indeed good because we have, I found 5 extra hours, but still I would like to confirm the lecture for next Wednesday, April 13. I'm going a lecture for 2 hours from 9 to 11. You may remember that I asked you for your availability. And I prefer to make this extra lecture because in this way, by making the extra lecture, I just would like to remind you that the week later I cannot teach, and also there is a missing week in May. So if I make this extra lecture, by the end of May, we will have still 3 extra hours. And these may be needed in order if you have your field trip. I didn't speak with the professor yet, but I think it's better if we keep 3 extra hours. And if you go for the trip, then it's no problem. If you don't go for the trip, I would cancel the last one. So I think it's indeed better. And I asked your availability for another date in May, another Wednesday. I think we can cancel that. It was, I think it was maybe May 11.
Yes.
Okay. Yeah, and I think we can cancel that, okay? So, to make a summary, next week we will meet on Wednesday 9/11, and then Thursday and Friday as planned. And next week, the calendar is that you will bring your PC on Friday. So you bring your PC tomorrow, and then next Friday, okay? And next week we will meet for 3 lectures. And then the week from the 17th to the 22nd, there are no lectures, okay? I think this should be all. Okay, perfect. Now, let me move to the lecture on rainfall runoff modeling, which was updated yesterday, but I think that there were no accesses so far. No accesses.
Excuse me, Prof, where are we going to meet on Wednesday?
Sorry? Sorry, I forgot to say that. On Wednesday, I will lecture in the room Trasporti. Do you know where it is? Yeah, everyone knows? No? Okay, it is in another building here. Basically, you have to get out into the internal courtyard that you get if you go the exit door that is located just below here. And then you go out from the internal courtyard and turn on the left. And then you will get yourself into the park. And when you get into the park, if you look on the right, there is an isolated building, a 3-floor building, a small one, yellow one. You have to go there. And if you don't find it, no, I think you will find it. But anyway, if you ask the reception, it's called Aula Trasporti. And it's there from 9 to 11. Okay. So, basically, I am, as usual, projecting the text here, but I'm teaching on the blackboard. And just as a reminder, we are dealing with estimation of the flood hydrograph. This is our current design variable, flood hydrograph, which I told you it's needed for designing reservoirs, everything that originates in storage. And I introduced the topic of rainfall runoff modeling as a possibility for modeling the flood hydrograph, and then I introduced the linear reservoir. And I said that the rationale of the linear reservoir is that the catchment is represented as a tank which is characterized by a state variable Wt and receives rainfall, which I call Pt, and then releases the river flow and therefore the hydrograph from a bottom discharge Qt. This is the scheme, the conceptual scheme, and I said that we are ignoring water losses in this first treatment. So there is no evaporation, no evapotranspiration, no deep percolation in the deep underground. Basically, the only water loss from this reservoir is that takes place through the bottom hole, the bottom discharge. And I told you that we need to be careful about the units here, because rainfall is usually given in millimeters per hour. First of all, there is usually a time step of the observations. So the observations are usually collected at a given time step. It may be daily, it may be hourly, it may be 10 minutes, sub-hourly. And typically you get the rainfall data which refer to this observational time step. And so at each time step you have rainfall entering into the tank. Rainfall is usually given in millimeters over time, so it may be millimeters per hour or millimeters per day. And then you get the storage. The storage usually is intended to be a water volume, and therefore it's expressed, for instance, in cubic meters. And then you get discharge, a river flow, which is given by a water volume divided by time, and usually it's given for rivers in cubic meters per second. So you have to be very careful on how to express these variables, and in the analytical treatment that now we will develop, I will make clearer how to represent and which units to use with these variables. And I told you that one, of course, this is a conceptual representation, but there is a physical basis which we always have to satisfy. And one physical basis, which is clear here, is the mass balance equation, one physical law that is underlying this system. And the mass balance equation can be written in this way. At each time step, I can write that the difference between the rainfall and the bottom discharge is equivalent to the change along time of the water storage into the catchment. So let's speak again about units. If you express rainfall, which is a rainfall intensity, so if you express rainfall as a length, rainfall depth over time, the proper unit to use here is meters divided by seconds. I say it is the proper unit because I want to express the proper unit here is cubic meters by second, divided by second. And I say this because cubic meters divided by second is the unit which I want to use for the river flow. So given that here I have a difference, if I want to express the river flow in cubic meters divided by second, I have to use the same unit for rainfall. And therefore, how can I express rainfall in cubic meters per second if it is given in millimeters per hour, for instance? Okay, so you have rainfall in millimeters per hour, which covers the catchment area. So first of all, you have to multiply rainfall intensity by the catchment area, and the catchment area is expressed by, I write here, is expressed typically in square kilometers. I use the unit because I want to write an equation with the units. So basically, if you want to get this product, you see that it's not dimensionally homogeneous, so you have to introduce a conversion factor. And the conversion factor is such that you have to multiply, first of all, by 1 million to transform the square kilometers in square meters. So here you have to write 1 million. And then you have to divide by 1,000 because you want to express millimeters in meters. Okay? And then you have to divide by 3,600 because you want to express hours in seconds. So I think this is the right conversion factor, which means that you can eliminate this and eliminate this. It's equal to 1 divided 3.6. Okay, this is the conversion in order to express rainfall in cubic meters per second. And of course, you have to multiply rainfall T times the catchment area times 1 over 3.6. Okay? Of course, 1 divided by 3.6 if you have the catchment area expressed in square kilometers and rainfall expressed in millimeters per hour. Of course, you may have different units. For instance, you may have inches if you work in a different countries for rainfall depth, and then you have to change the conversion factor. Computing the conversion factor is a very easy and simple operation, which we usually get wrong about 95% of the times. So be careful about this, because it is indeed, from a technical point of view, it is an obstacle, because it's easy to make mistakes, even if it is easy to make it, because you see that basically you just have to convert the units, and it's very easy to make. But on the other hand, it's easy to make mistakes. So be careful about that, because it's very frequently when we make our exercises and we see the results of our programming, very frequently the reason of the mistakes that we get is an error in the conversion factor. So be careful. Okay, so basically, if you express in cubic meters per second rainfall and river flow, then W is expressed in cubic meters, because it's divided by time, and therefore it's just enough to express W in cubic meters. So this is, of course, a physical law that we need to meet, and it's a physical law that we can use to compute our unknown, and the unknown is Q. But, as I said when I closed the last lecture, it's not enough, because we introduced another unknown, which is the state variable W. So we need a second equation. And the second equation, a candidate, is a relationship between the bottom discharge and the water storage. And if we introduce this kind of relationship, it's an energy equation. It's a conservation of energy equation. Because you may remember, if you took fluid dynamics in your undergraduate courses, that there are some laws regulating the discharge from a tank, a water tank, the bottom discharge. So if you get a real water tank with an assigned water level inside it, and you make an hole in the bottom of the tank, you have, of course, water flowing out. And you may remember a law which is called Torricelli's law, that gives to you the velocity with which the water flows outside, depending on the water depth into the tank. And this Torricelli's law is derived through an energy balance equation. It's your intuition that if you have a higher water storage into the tank, then you have a higher discharge from the bottom. Why is that? Because, of course, water is making pressure. And basically, why you have a discharge from the bottom? Because the potential energy of the water that is basically is basically static into the tank. Water has a potential energy, and this potential energy is converted into a kinetic energy of water flowing out. And therefore, the more water you have into the tank, the more potential energy you have into the tank, and the higher is the velocity, and therefore the outflow from the tank. So basically, it's an intuition. It's quite a clear intuition that if you introduce a relationship between QT and WT, it's an energy balance equation. I could prove it, but it takes about 15 minutes, and it's a typical fluid dynamics subject. So I would prefer not to go into the details, but if you go to Wikipedia, I may make a link here, and you look for Torricelli's law, you get the explanation. Let me make just an experiment to see if it is there. Yeah, you see here. Of course, it's a usual subject, and here is the explanation of Torricelli's law, and you will see that it's an energy balance equation. Energy, kinetic energy. Okay. And I will put a link on this, but you can easily find it as you saw. Okay, so basically let's introduce the second equation. And the easiest thing that we can do is to introduce a linear relationship. So let me write that QT is equal to WT. And of course, there is a direct proportionality. If I assume that the relationship is linear, there is a direct proportionality. And you know, I need a proportionality because I said that for increasing water storage, I must have increasing river flow. But in order to ensure that they are dimensionally homogeneous, I have to divide this water storage by a time. And what is this time? This time, it's a parameter that I call with the symbol K, and let me assume that this is a parameter. Please remember what a parameter is. Is an element into an equation that is usually constant, which doesn't change the shape of the equation, but gives flexibility to the equation. And I need this flexibility because you know, this is a model which needs to be adapted to a real process. And it's better, it's advisable to introduce some flexibility, otherwise the model could not adapt to different catchments. And so far I didn't introduce any flexibility. In the first equation, which is this one, there is no flexibility, no parameters. So in this second equation, it's better to introduce a parameter. And I said that it has a dimension of a time. It must have it. Because in order to make this equation dimensionally homogeneous, it must have it. It must have the dimension of a time. And I want the relationship to be linear. And you know, for varying values, for varying k values, it remains linear, the relationship between Q and W. The important thing is that K is not time dependent. If K was time dependent, the relationship wouldn't be linear anymore. Let me remind you what is a linear relationship. I think I didn't recall this definition, or maybe I did, but it's better to recall what is a linear relationship. A linear relationship, I need to make some room. I think I can delete here. So let me, in order to make some room, let me rewrite this equation up here, or maybe below here. Okay. What is a linear relationship? So basically, let's think about a function fx. The function is defined to be linear if two conditions are satisfied. The first one is that fx plus y is equal to fx plus fy. And the second is that f ax is equal to afx. These are the two conditions that make a relationship linear. So basically, in our case, it means that the first condition means that if you have two rainfalls, and you want to know the river discharge for the sum of the two rainfalls, and the two rainfalls will be x and y, basically you can compute the river discharge from the x and the river discharge from y and sum them. So if you have two rainfall impulses, in order to compute the river flow given by the sum of the two pulses, you can take the sum of the river flow given by each of the pulses, which is not true in general. If you have two rainfalls, you cannot get the river flow as a sum of the individual responses to the two rainfalls. Why is that? Because I already told you that the reaction of a catchment to a rainfall depends on the antecedent condition, on the soil moisture condition. So the reaction is different depending on whether it rains over the wet soil or dry soil. And therefore it's not, in general it's not true that the superimposition principle, this is the superimposition principle applies. Basically, from a technical point of view, we can say that for a linear function, the superimposition principle applies. This is, and you may ask me why we take a linear relationship if in general it's not satisfied. The reason is simplicity. You will see that by taking a linear relationship between river flow and the water storage, we can integrate analytically these two equations, or let me say that under certain conditions we can integrate analytically the two equations. And it was, I already mentioned to you, it was important. Just 10, 15 years ago, the analytical solutions were very important. So people tried to devise analytical solutions. So this was the reason why they preferred to adopt a linear relationship. Okay? So if we adopt a linear relationship here, we can combine these two equations, because I can substitute for W in the first equation the expression given by the second equation. The second equation can be written as Wt is equal to Kqt. Okay? So basically I can express the second equation in this way, and then I can substitute here, and therefore I can write dt minus qt is equal to this to the t of k qt. And then let me divide by k, and I can write 1 over k times rainfall minus 1 over k times qt river flow is equal to the derivative over time of qt. Sorry, it's a bit, I hope everyone can see here, but I'm not sure. So let me delete this sketch here. And let me rewrite the equation here. 1 over k qt minus 1 over k qt, sorry, is equal to the derivative over time of qt. Yeah, and I can delete this one. Perfect, so we have this equation. So please pay attention to what we did. We combined the two equations into one. And so you may say, but what I'm losing here? Because I had two equations before than that, and now I have one equation. So you may feel that we are losing something. At the beginning I said that we had two unknowns, and then we needed two equations. So you may feel that, again, we are losing something. Actually, we are losing the description of one of the unknown, which is W, which we substituted. So basically, given that we are not really interested in getting an estimate of the state variable, because it's a state variable, it's just a, let's say, a tool that we introduce. We are not interested in it. Then, if we are not interested, then we can combine the two equations, and by combining the two equations, we lose an unknown. So we now have just one unknown, which is the river flow Qt, and then we need one equation to describe it. So we are not losing anything but the description of Wt. On the other hand, I may say that if you're interested in knowing Wt, it's not a problem. Once that you estimated the unknown Qt, you can easily get an estimation through this second equation of Wt. So if you want to know it, no problem. Okay? Now we have this equation, and now our task, our mission is to get an explicit representation for Qt. And we can do it analytically. I think it is instructive. Actually, you know, you will see that at the end of the story tomorrow we will apply a numerical solution for this model. But still, I think it's very important to understand the analytical solution. So you can see the difference between an analytical solution and a numerical solution. And you can see pros and cons, advantages and disadvantages of each of them. And I think that for one time it is useful to make some discussion and some reflections on a comparison between these two approaches. And then this is the last time that we will make an analytical solution in, I would say, for the full subject. But I think that once it's useful. So how can we, the problem is that we need to make an integration. We are engineers, so we are not very familiar, at least in Italy, we are not very familiar with the integrals and derivatives. And maybe with derivatives some, but with the integrals, you know. So we will try, I'm trying now to integrate it, and we try to not to make mistakes and to go slowly. So basically, in order to integrate it, first of all, let me multiply both sides by e to the power of t over k. This is a strategic move. You will see that by doing that, I will simplify things. So basically, I can write 1 over k pt minus 1 over k e to the power of t over k times qt. It's equal to e to the power of t over k derivative of qt I just multiplied both sides by e to the power of t over k. Okay, now let me make some room here. And now let me bring, in this equation, let me bring every term referring to q on the left-hand side, and the only term referring to p to the right-hand side. So I'm just moving. So basically, what I would like to do is to write here e to the power of t over k, which multiplies the derivative over time of qt. plus 1 over k e to the power of t over k qt. This is equal to 1 over k e to the power of t over k pt. So I separated the variables, and you see that I moved the term and I changed the sign. Okay, so this term was on the right-hand side, it was brought to the left-hand side, and I changed it. I kept the sign, so I changed the sign of the whole equation. And the same thing here, this was negative, it remains on the same side, so I need to change the sign. And for this one is positive, but it changes the side, so I keep the same positive sign. Now, if you look at the left-hand side, this can be written as the derivative over time of qt times e to the power of t over k. It's the derivative of a product between two functions, and you may remember that this derivative is equivalent to the sum of two terms. The first term is obtained by taking the derivative of qt here times the second term unchanged here plus the first term unchanged here times the derivative of the second term e to the power of t over k, and this derivative is equal to the same term e to the power of t over k times the derivative of the exponent, which is 1 over k. Remember that k is a constant. So I hope it's clear that I can write this term as the derivative over time of the product between qt and e to the power of t over k. And then this is equivalent to just 1 over k. I'm copying by keeping it unchanged. 1 over k e to the power of t over k times precipitation pt. And then I'm ready to integrate both sides a long time. Why I am integrating now? Why I need to integrate? I need to integrate because this is, sorry, probably I'm saying a trivial thing, but I think it's important to make clear the physical meaning of what we are doing. And I am integrating because this is a differential equation. So it describes, as you can see, the derivative over time of the river flow. But I am not interested in describing the derivative. I need to describe the river flow. What is the derivative? The derivative is the change of the river flow at each time step. So the derivative has a very clear significant, physical meaning. It's the change on the river flow at each time step. I'm not interested in describing this change of the river flow. I am interested in describing the river flow. And how can compute the river flow then? By summing the changes. I need to start from an initial condition, a given Q, and then at time t0, which typically is the beginning of the simulation period, the beginning of our hydrograph, and I need to start from a known initial condition because this equation describes the changes. So I need a starting point, and the starting point is called in mathematics initial condition. So I need to fix an initial condition, and then I need to sum the changes. And what is in mathematics terms, the meaning of summing the changes expressing by a derivative, it's an integral. So I need to integrate the changes to compute the river flow. And of course, I will need an initial condition. The initial condition could be Q equals 0, for instance. Or, if you have an observation telling you that at the beginning of the hydrograph, the river was characterized by a given river flow, then you take that observed river flow as the initial condition. So when I say that I am integrating, I need to integrate because I need to sum the changes, and I am implicitly underlying that I need an initial condition. Okay, so let me compute this integral. And the integral is, as I said, an integral over time. So I need to specify, because this is a defined integral, it's not undefined. And I need to specify the timing of the integration. And the timing of integration means basically the length, the time length of the hydrograph that I want to simulate. So the timing is between 0, let me call the initial time 0, and a given time t, which is defined by u. So I need to write above here, so please let me, or I may cancel here, it's better. Okay, so now I just write the integral sign. The integral sign is between 0 and t of the derivative. So this is an integral of a derivative, and it's easy to compute because the integral of a derivative is the argument of the derivative. But let me write the derivative here, and it's qt e to the power of t over k in okay, in basically